We stopped at, we looked at the star delta, delta star transformers. I just wanted to summarize today, right? So anytime we have a star star or a delta delta transformer, converting to a single phase equivalent circuit is easy because the voltages on the primary and the secondary are in phase, whether they're the line voltages or they're the phase voltages. Even if it's a delta delta, the line voltages are in phase, which means that the corresponding phase voltages will be in phase, right? So star star, delta delta, no problem. Star delta is when we start having issues, and in per unit, the resultant is, or the resulting transformer that you will use in the single phase equivalent circuit is still a one-to-one transformer from a magnitude perspective, except that there's a angle associated with it, and it's 30 degrees for star delta and delta star transformers, and the high voltage side leads by 30 degrees. So it's always the high voltage side leads by 30 degrees. This is in per unit. Per unit, so it's the magnitudes are still 1 to 1. But before converting to per unit, we talked about the effect of turns ratio and how we derive this 30 degrees, right? Summary of that is the following, okay? That the turns ratio, the way I would like you to study it or use it is 1, 2. This is the high voltage side, right? It leads by 30, right? So 1, 2, number of turns on the high voltage side over number of turns on the low voltage side, square root of 3 e to the j30. If you remember this, then that's all you need to remember, really. Anytime you have the high voltage side, put the high voltage, obviously the high voltage turns would be greater than the low voltage turns. So this is a number greater than 1. In the textbook, they use n primary over n secondary. You can use whatever they use in the textbook. I don't have a problem with that. But sometimes when you have a delta on the primary and then a star on the secondary, so the star is the high voltage side, and you use the n primary over n secondary, you will have to use it on this side, right? You will have to, because it's a number smaller than 1, right? So an easy way to remember, and if you want to remember just one thing, this is what you need to remember. This is what you put on the high voltage side, and it will always work. Right? So that's sort of a summary of what we discussed last time. So any questions on that? So of course the impedance transformation from primary to secondary still applies, and you do not change the angle of the impedance, right? And since it's a one-to-one ratio from a magnitude perspective, then you just bring, from a per unit perspective, the impedance in the primary is equal to the impedance in the secondary, right? Nothing changes, right? But voltage and current magnitudes also don't change in per unit. What changes is the angle. So if I have a voltage here, they tell you the load voltage is, 1 angle 0. This is leading by 30 degrees. So for you to bring everything to the primary side, it's like, let's say you have a voltage source here and they're telling you this is a load with 1 angle 0 here. To bring it to the primary side, you will have something that looks like this, the same load, but one with an angle of minus 30, exactly. Right, so that's the same thing with the current. You calculated the current here of I with an angle of, I don't know, this is minus 20. That's a lagging load, lagging power factor load. So the current here into the load will also be I minus 20 minus 30, right? And that's it. Really, it's nothing more than that here. Okay. So let's, I think we'll do some examples today, and then we'll move to some new material. Yeah, that's the objective of today's class. Yeah. So this is one example. So we have a delta Y step-up transformer. So the delta is the low voltage side, right? The star here is the high voltage side. So it's telling you it's a delta Y step-up transformer from a generator load, right? So given a three single-phase transformer connected to form a three-phase transformer. The three-phase transformer is rated for 23 kilovolts on the primary, these are the terminal voltages, right? Terminal voltages of the transformer on the primary. Terminal voltage of the transformer in the secondary is 230 volt rating, right? That's the rated voltage primary in the secondary. And it's rated for 100 megavolt ampere. And the transformer has primary leakage X1, so X on the primary side, in real values equal to 0.21, right? So that's the transformer on the leakage. That's the primary side reactance, right? In real values, right? And then on the primary side, I have a star or a delta. Delta, right? So what does that mean? I remember I'm going to be drawing my single phase equivalent circuit to solve. So what do we do about the delta impedances? Divide by 3, right? So I will have to, this is my transformer impedance. I will have to divide that by 3 to put it into the single phase equivalent circuit, right? So a transformer is delivering 100 megawatts at 0.9 power factor lagging. I have too many givens here. To a substation bus whose load is 230 kilovolts. So here, this bus here has a voltage of 230 kilovolts and is consuming 100 megawatts at 0.9 power factor lagging. Right. So let me write all these givens down. So we have 23, 230 kilovolt, 100 MVA transformer. X1 is equal to 0.21 ohm. It's delivering 100 megawatts. Load 0.9 power factor lagging. The bus voltage is 230 kilovolts. So before looking at the solution, let's see what we can sort of do with the information we were given here. So we have a system that looks like this. We have a generator, and then a transformer. It's a bus bar here, right? My transformer, and then I have another bus bar connected, and a load connected at the bus bar. So the load, they're telling us that the load is 100 megawatts. P load is 100 megawatts. This is, of course, for the three-phase load, right? When they don't specify it as a single-phase load, then of course it's a three-phase load, since they're talking about the power system. So P is 100 megawatts. It's 0.9 power factor lagging, and the V at this bus, so V load, again, they're also saying it's 230 kilovolts, and they're not specifying anything, so it's a line-to-line voltage. So V load is 230 kilovolts. This is a line-to-line voltage, right? What else? And they're saying that this transformer is a 23 kilovolt to 230 kilovolt transformer. They're saying it's a delta star, and it's 100 megavolt ampere rating, and the primary reactance is 0.21 ohms. Okay, so we sort of have everything given. However, yeah, I know this problem. So in this problem, what they're asking for what? Find the primary voltage, line to line, current, and three-phase complex power supplied by the generator, and find the phase shift, I guess, of the generator. Generator's voltage or current. I'm not sure what they mean by find the phase shift, honestly. It's not very well written. Find the phase shift of what, right? So, sorry, yeah.
213 kilowatts, you said it was line to line, but I mean on the delta side, wouldn't it be line to neutral?
No. This is a 223 to 230 kilovolts. These are terminal voltages. Okay. Terminal voltages is the 230 volt is on the star side.
Yeah.
So it's the line-to-line voltage on the star.
Line.
Line to line.
Okay.
So the phase voltage would, if you want to draw the single phase equivalent circuit, would be what on the star side?
Multiplied by the square root of
Exactly, right? But on the primary side,
the-
this line-to-line voltage is 23 kilovolts. If I want to draw the single phase equivalent circuit of the primary, I would have to take this 23 kilovolts and do what? Think of a fictitious star that's connected and deduce what the phase voltage would be, right? But what would the phase voltage be? Also 23 kilovolts divided by 30, phase shifted by 30 degrees. The line voltage is leading by 30 degrees, so you have to lag it, something lagging by 30 degrees, right? So line voltages lead phase voltages by 30 degrees. So here I'm given line voltage, and this is leading the phase voltage by 30 degrees. And it's square root of 3 greater than the phase voltage, right? So the single phase, let's draw it and then look at what values they're putting. The single phase equivalent circuit that we have for this is what? We have a source, generator, and the generator, they didn't give us the impedance for a generator, so we assume it's just a voltage source. And then we have what? They gave us the impedance for the transformer in real values. So let's see if we need to convert anything to per unit. They didn't ask us to convert to solve this problem per unit. So if they don't ask you to solve it per unit, you don't need to solve it per unit. You don't have to solve everything per unit. You don't have to, right? But if I give you this in per unit, then you need to come up with all the bases and right. So this was given in real values. So this is an impedance that I put in series. They don't give you an impedance for the transmission line, so there's nothing there, as if it's not there. And then they give you the receiving end or the load, right? But they also tell you that this is the delta star transformer. So I put its impedance here, and we said that since this is the impedance on the primary side, and this was a delta on the primary side, then we have to take this impedance. So x1 is equal to 0.21 divided by 3, right? So since this was the impedance of the transformer on the primary side, and it was a delta, so I take that impedance divided by 3, right? And then it's a delta star transformer, so I have to account for phase shift. So I have to include a transformer in there, and then they give you the load specs. This is 100 megawatts, 0.9 power factor lagging, voltage is blah blah blah, right? And this is the low voltage side, and this is the high voltage side. So right, this is the low voltage side, this is the high voltage side. So this is always going to be leading by 30 degrees. This high voltage side will be leading by 30 degrees in a single phase equivalent circuit. So let's look at the turns ratio. Let's look at the turns ratio of this phase shifting transformer, right? So what is the turns ratio of this phase shifting transformer? I suggested you to use 1, 2, number of turns on the high voltage side. So I can use 230. So number of turns. This is the terminal voltage, not the number of turns, right? So number of turns on the high voltage side. Let's see if we solve for that later. But over number of turns on the low voltage side, square root of 3 e to the j 30. And here they tell you this is 230 kilovolts line to line, and they give you the power factor and then they give you the power. So let's see. So we can draw the power triangle for the load, right? So I have my real power, that's given, that's 100 megawatts, right? And they give you the power factor for the load, so I can sort of draw this line. So this angle is equal to minus inverse cosine 0.9, right? So I have this angle. So given this angle, so since you have this length, and you have this line here, just from geometry, you can extend this and bring it here, which means that you can use your triangular Pythagorean theorem to figure out what S is and what Q is, which means you can also do what? S equals V times I conjugate, right? Which means you can also calculate the current here, right? And since I have the current here and the voltage here, and if I figure out what this turns ratio thing is, then I can bring the voltage and current on the primary side. Or if I convert this to per unit, again, I don't know what the solution will go through, but if I convert this to per unit, for example, then this turns ratio becomes a 1-to-1. I just have a phase shift, right? And I have voltage and current on this side, and I can bring them easily on this side by just phase shifting the quantities, right? If I just phase shift the quantities, if I converted it to per unit, phase shift the quantities, and everything is done, right? So let's see how, and then if I bring current here, and I have the voltage on this side, then the current multiplied by this drop will be this voltage here. Take this voltage, add it to this voltage, and you should get the voltage produced by the generator, right? So is this what they're asking for? Let's see how they're solving it here. So, but does everybody see the logic of what we are going through, of this problem? So let's see. Okay, I don't like one thing already, but I'll tell you what it is. So here they put this as 10. Can somebody tell me why? They divided basically the 23 by 230. But they did that only because they said that they assumed that this is the turns ratio for the single phase transformer. So because they said given 3 single phase transformers connect to 3-phase transformer, this one is a bit confusing as well, right? So if they said that this is the turns ratio for the single phase transformer, I agree with putting the 10. But what if they didn't say? What if this is the rating of the 3-phase transformer, 23 kilovolt to 230 kilovolt? What if it is the rating of the 3-phase transformer? Then what? Let's go back. If we go back, we see that for us to figure out the turns ratio of a star delta or a delta star transformer, the turns ratio is what is defining the relationship between the phase voltage on the star and the line voltage on the delta. Is everybody clear with that? The turns ratio itself is defined by the ratio of the phase voltage on the star, and which is VAN capital here for the star, and the line voltage on the delta side. Does everybody see that? That's defining the turns ratio only, the actual number, the ratio of the actual number of turns, right? It's not the terminal voltage, because the terminal voltage here is capital VAB. That's the line voltage on the star. The line voltage on the star and the line voltage on the delta are not related by the turns ratio. They're related by the turns ratio multiplied by square root of 3 multiplied by the phase shift of 30 degrees. Does everybody see that? Yes? No?
Yes.
Yes? Okay. So they said that this was a delta star transformer. So our turns ratio for the new equivalent transformer should have the actual physical turns ratio, the square root of 3 and the 30 degrees. Fine, here they put them on the primary side, on the delta side. So they rotated e to the minus 30 and they divided by square root of 3. Right? So if I want to, if I have a delta star versus a star delta, right? If I do this, they're saying that we said that the star is on the high voltage side, so it will lead by 30 degrees, right? But they want to write everything on the with respect to the primary's voltage. So the delta is doing what? Lagging by 30 degrees, right? And the star was square root of 3 greater. So the delta is on the single phase equivalent of the delta psi that we would plug into the single phase equivalent circuit is less by square root of 3, right? So if this was e to the j 30, so it's leading by 30 degrees, and it was n primary over n secondary, and it was square root of 3 to 1. This was the ratio for the star delta transformer, right? Go back to the star delta. Yeah, star delta transformer, square root of 3, the turns ratio for this transformer, square root of 3, n primary over n secondary, which in this case was the star side to the delta side, e to the j30, right? That's what I wrote. That's what I wrote here. N primary over n second, e to the j30, square root of 3. All on the star side versus 1 to the delta side, right? If I would like to bring these on this other side, right? I just want to change the turns ratio. I mean, the turns ratio will remain the same. The ratio will remain the same. I just want to, instead of writing 1 to 2 as the transformer ratio, I write what? 1/2 to 1. Right? This is still half of this. This is double this. Right? It doesn't matter. If you take these quantities on this side, divide them by the quantities on the primary side, you will put 1 here. Right? So I will do the same. I can do the same here. I can write for the delta. I can write that the delta is lagging by 30 degrees, e to the minus j30th, and n primary over n secondary will remain the same, and that's why I told you it's better for me. I would recommend using n high voltage over n low voltage, because in that case you don't get confused at all. Okay, and then do what? And then divide it by square root of 3. So bringing down the square root of 3, bringing e to the j30 down. But remember, the delta and the star switch places here. So this is n primary and this is n secondary. This is n primary in this case. This is n secondary in this case. Right? So n primary is what? In this case, it's the low voltage side. Right? And here, n primary here is the low voltage turns equivalent. Versus n primary here is the high voltage turns equivalent, right? So that's why for me, if it's a delta star, anytime you have a delta star, the high voltage side, put the n high voltage or n low voltage, right? You get this or not? Right? So it makes it easier. For me, it's better than memorizing, okay, n primary or n secondary, fine. In this case, the primary is a delta versus a star. I would just, okay, all the time, put these on the star side. And n would be the n high voltage versus over n low voltage. In that case, there's no confusion. Right? So in this example that they gave, they sort of assumed that this was the rating of the single phase. These were the terminal voltages of the single phase transformer. So if these were the terminal voltages for the single phase transformer, then I have n primary over n secondary, or n high voltage over n low voltage is equal to what? 230 over 23, which is equal to 10, right? If this was the rating for the single phase transformer voltages here. You're okay with this? If this was the rating for the star delta transformer, then I'm missing some information. Because now I have the terminal voltages, but I don't have the turns ratio. So how do you calculate the terminal voltages from the turns ratio? How? Yeah, 30 degrees will be there, right? But from a magnitude perspective, what? I have 1 on the high voltage side, so 1, 2, and high voltage, or 1, 2, this. I'll call this X. 1 to X is equal to, in this case, 23 over the 230. Right? So what will be the X in this case? Hmm? Is it 20? Is it? Let's look at here. I'm sorry, the wording of the problem is very poor here. It was a delta star, right? Where's our delta star? This is my delta, and the voltage is, the line-to-line voltage is what? For the delta, they said it was 23 to 230. They assumed it was the single phase voltages, for the voltage, the terminal voltage for the single phase transformer. So the 10 is justified, okay? That's where they got their 10 from, okay? But I'm saying that what if it was not? What if this was given as a delta star transformer with a 23 kilovolt on the primary and 230 kilovolt on the secondary? How do you find the turns ratio? So basically this voltage now is 23 kilovolts, right? What is the magnitude of this voltage? Right? These two voltages are in parallel, meaning these two windings are in parallel, so they're in the same core, right? So what is the voltage of this? We don't know that yet. What we know is that this is the terminal voltage on the primary, this is the terminal voltage on the secondary. Terminal voltage on the secondary is this is the terminal voltage on the secondary. So this was VCA, so this is the VCA. VCA is 230 kilovolts. So what is VC?
It's 23 over.
It's 230 kilovolts over the square root of 3,
Why is it 230 not 2?
lagging by 30 degrees. Lagging the line voltage by 30 degrees. Minus 30, assuming this was angle 0. Right? If I just want the magnitude, then it's the magnitude of it is 230 over square root of 3. Why is it?
Not 23.
No, because I said the primary the terminal voltage on the primary is 23. Okay. Terminal voltage on the secondary is 230 for this transformer. So it's a step-up transformer.
Also use the 230.
Okay. So now what is the turns ratio? So this is now where the voltage on this winding. So now what is the ratio of N primary to N secondary? M primary or V primary is 23 kilovolts. V secondary is 230 over square root of 3. Right? So I bring it up, so it's 23 times square root of 3 over 230. That is equal to what? Or 230 over 23 times 230, yeah. 23 square root of 3 times 230.
0.17.
So 1 over 0.17 is, the turns ratio is 5.88 or 1 over,
The whole thing is 0.17.
Yeah, 0.17, sure. This is 0.17. If I want n secondary over the 0.17. So what if I want the n high voltage over n low voltage? It's the inverse of that. So that's why it's n1 over that, and it's equal to 5.88. Right? So it's, instead of the 10 that they used, we would have used 5.88. Do you see the difference? Just one word can change in the problem. This problem is not worded properly, but the good thing, the fact that it's not worded properly made us look into this, right? So now, this is how you would calculate the turns ratio if you are told that it's a star delta transformer or a delta star transformer with these terminal voltages. But if you are told, if you are told that this is the terminal voltage of the single phase transformers that are used to construct a star delta transformer, different numbers, you would use 10, right? Because the turns ratio of this winding to this winding in that case would be 10, because this was a single phase transformer that you took and built the three phase transformer with. Is it clear? Okay. Do you all get this? That, you know, the physical turns ratio is the ratio of the voltage of the two windings that are on the same core, right? That we get. That is the physical turns ratio n primary over n secondary, given the primary here is a delta and the secondary is a star. Physical turns ratio n primary over n secondary is this voltage over the voltage of this winding. I'm telling you that you are given a transformer, a delta star transformer, that is rated for 23 kilovolts on the primary terminals and 230 kilovolts on the secondary terminals. That's the terminal voltage of this transformer is 23. Terminal here, this is terminal voltage. Terminal voltage, right? This is the voltage between the two terminals A and C, 23 kilovolts. And the terminal voltage on the secondary, again, this is VCA, then I go VCA. VCA is this voltage between terminal A and terminal C. VCA is 233 kilovolts. That's the terminal voltage of the transformer. What is the turns ratio? Because remember, for us to draw the transformer and draw a single phase equivalent circuit, not in per unit, right? Not in per unit. To draw a single phase equivalent circuit, I need to do this thing: 1, 2, n high voltage over n low voltage, square root of 3 e to the j 30. Always, this is the high voltage side leading by 30 degrees, so I would just always n high voltage over n low voltage, instead of this n primary over n secondary. But again, you can do whatever you want here. You can just use the equations if you wish. But I need to apply this. For me to apply this, I don't know what this is for a star delta transformer. I know it if they tell me that I was given 3 single phase transformers. Remember the star delta transformer, we built it last class with 3 single phase transformers and we connected the windings in delta, right? If I'm telling you that the ratings of the single phase transformer are 23 to 230 kilovolts, then n high voltage over n low voltage is equal to 230 over 23, which is 10, right? But if I'm telling you that you have a delta star transformer with terminal voltages equal to 23 to 230, these are the terminal voltages of the delta star transformer. This is not what you need to plug in here. Okay? There's a square root of 3 that you need to take care of. So why? Because these two, in that case, in the case of this being a transformer, a 3-phase transformer with such terminal ratings, then this is 23 that they're telling you about, and this is the 230 that they're telling you about. Then in that case, the actual turns ratio of the transformer, which you need to plug in here, is what? Is this 230 divided by square root of 3, which is the phase voltage that you have on this phase, and then this and this are the ratio of these two is what gives you the actual turns ratio that you plug into the equation. Okay? Yes.
Wouldn't it here be, okay, so N high voltage over N low voltage is 230 over 23 squared root of 3?
What
N high voltage over N low voltage
is
200
30
over
over 23
square root of 3.
square root of 3? And yes, and you will be multiplying by square root of 3, and they will go away, and you will end up with 10.
But then,
Sir, but what if I ask you what the turns ratio is of the transformer? So that's why they use 10. So they use 10. So I agree. So, but I was asking what the turns ratio is of the transformer.
Okay.
I was trying to justify the 10, and yes, when I did this, right before you just did it, yes, I realized that it will also be 10. But if I ask you what the turns ratio is,
Okay. So what's the difference between the turns ratio then and that? What is that, the 1 to? Because I thought that was the turns ratio.
what do you mean?
The 1 to.
No,
N
the
one-
turns ratio is n high volt or n primary over n secondary.
Okay. So what? Okay.
This is the turns ratio.
Okay.
The fictitious turns ratio of the transformer, of the equivalent single-phase transformer, is 1 to n high voltage over n low voltage times square root of 3 e to the j30.
Okay.
That's the, I mean, there's no transformer that has a turns ratio. If you don't have two single-phase, you cannot phase shift by using two single-phase windings. Right? Two single-phase windings will produce what? If current's coming in here, current's coming out here, voltage here will be in phase with the voltage here, as long as the dot notation is the same, right? So we have to use a fictitious turns ratio, T, that they use is T, instead of A. A was the actual turns ratio of the transformer, right? So there's a difference between the actual turns ratio of the transformer and this equivalent turns ratio of the transformer that is used when you have a star delta or a delta star or any other phase shifting transformer. Okay? So there's a difference between them. Right? So there's a difference between the physical turns ratio and this fictitious turns ratio used in the single phase equivalent circuit. Does everybody get that? So fine, they will end up using the same. You will end up with the same number here, but here no, it's not the same number because here they 10 and multiplied by square root of 3. That's wrong, right? So what I'm saying is still valid, right? Because for us, we would have put here what 230 over 23 square root of 3, and then that is what? That would multiply by square root of 3, and that would result in 10. Here they have 10 times square root of 3, right? So it's because they are telling you that 23 to 230 is the rating of the single phase transformer itself, not the rating of the star delta connected transformer. Okay? There is a difference.
They're still multiplying by root 3 because of the phase alignment?
They multiply by root 3 because we said our fictitious turns ratio is n high voltage over n low voltage times square root of 3 times e to the j30. That is always our equivalent turns ratio whenever we have a delta star transformer, right? The only issue is this number 10. Okay, this number 10, they used it as 10 because of the assumption that this 230 to 23 to 230 is the turns ratio of the single phase transformer. I'm saying, what if they don't state it that way? If they state it as this is the terminal voltage of the delta star transformer, how do you solve it that way? This is correct. This 10 times square root of 3 is correct, assuming that this was the turns ratio of the single phase transformer. If it is the delta star transformer, it is not. It is 5.88 that we got multiplied by square root of 3. So both of them together would be the 10, not 10 times square root of 3. Does everybody get this? Right? That's a bit confusing. But after that, what after that? It's very simple. So now you have the turns ratio. You were given the voltage here as what? 230 kilovolts, right? We were given the voltage at the load as 230 kilovolts, 0.9 power factor lagging with 100 megawatts. So we were able to calculate the voltage at the load here. So we know the voltage and we know the current at the load. Now we need to take this voltage and current, bring them to the primary side. This current will be, you take this current and do what to it? Not just phase shift. You have to phase shift and take care of this. So the voltage was stepped up. So here, low voltage to high voltage, right? High voltage, low current. Low current will go to the primary side as high current, right? So you will take this current, multiply it by 10 times square root of 3, and delay it by 30 degrees. Okay? So we stepped up the voltage and we stepped down the current here. So that means we have to step up the current and step down the voltage. Right? So multiply the current by 10 times square root of 3 and divide the voltage by 10 times square root of 3. Okay? So let's see if they do that. So after you do that, we brought the current and voltage to this side. And then we have our impedance here that they gave for the transformer. They didn't give a generator impedance. They didn't give it a generator impedance, so I'm assuming that this will just be dropped. They will not consider that, I think. And then they ask for the generator's voltage or current or phase angle or whatever. Let's see what they do. So VAN prime is what? 230 angle. Yeah. So this, the voltage A prime, N prime, is what they are saying are the 230 volts divided by square root of 3. Right? So why is that? They assume it's a line voltage. It's very weird, yeah. So they assume that 230 volt was the line voltage, right? Divide that by square root of 3, then it becomes the phase voltage in the single phase equivalent circuit, right? Which sort of defies the fact that they assumed it was the single phase transformer's terminal voltages initially, right? So there's a typo there's a problem with this. There's a typo here where and you cannot use a 10 here and then assume that the 230 is your phase voltage, right? So here they assume 230 over 23 was the phase voltage of the single phase transformer. So the ratio between the primary and secondary was 10. And that's what they used here, 10. Right? But then they said that if 230 was if the ratio was 10, that means that the 230 is the actual phase voltage of the star. Right? But they don't do that. They go and say it's 230 divided by square root of 3. Right? So I will delete this problem from the set of slides. But again, it's good to go through it now that we see the problems that we have with it here. So assuming it is the line voltage, we take that. So if we assume it's the line voltage, then the only mistake here is this 10 becomes 5.88. Okay? So let's assume this 10 is 5.88. Everything else will be the same. So we take our 230 volts, which is the line voltage, then divide that by square root of 3, which is 132.8 kilovolts. So 132.8 kilovolt is the voltage I have on this side here. Right? That's the VAN. VA prime, N prime voltage. Right? And then they use 100 megawatts. So they want to calculate, again, the power in single phase power. So they take the full power at the load, divide that by 3. So then you have the single phase power, single phase S. Right? You take S and divide it by the power factor. You divide it by 0.9. So you take the single phase power single phase P, divided by, so 100 megawatts was a 3-phase power. Divided by 3, you get the single phase power. Divide that by 0.9, you will get S from the power triangle at the load. The load is 100 megawatts. This is angle theta. Cosine theta is equal to 0.9. Cosine theta is equal to the adjacent, which is the P, over the hypotenuse, which is S, right? It's equal to P over S. So S is equal to P over cosine theta. If this is S three phase, this is P three phase. If this is S single phase, and this is P single phase, right? So they decided to, because we want to build a single phase equivalent circuit, not in per unit, right, in actual values, then what we need to do is calculate the power for single phase. So they took the P, which is 100 megawatts, right, and divided that by 3. Remember, I have to add the power, and the power in actual quantity is not per unit. You have to consider the multiplication by 3. So to power in single phase is equal to the power in three phase divided by 3. That's where the 100 divided by 3 comes from. And then cosine theta was 0.9. That's given in the problem. So that's where they calculate the S, single phase apparent power. Given S and V in single phase, you should be able to calculate the current. S is equal to V times I conjugate. So they calculated the current, the conjugate of the current, and hence the current, you just flip the angle, right? So you put a minus sign here to basically flip it 180 degrees, right? So the conjugate of the current is equal to 278.9, angle 25. The actual current is equal to 278.9, angle minus 25.84. Okay? So it's lagging the voltage. The voltage was angle 0. They used it as a reference. The current was lagging by 25.84 degrees. Now I want to bring this where? To the primary side. For me to bring this to the primary side, we said that I have to multiply by the turns ratio that we have, the equivalent turns ratio that we have. So I will have to phase shift by 30 degrees. Where? So I'm moving from the high voltage side to the low voltage side. High voltage side leads by 30 degrees. So then if I want to go to the low voltage side, I do what? I have to subtract 30 degrees from the angle. So this minus 25.84 is going to be what? Minus 25.84 minus another 30 degrees. So it's going to be minus 55.84. And that's what we should have somewhere. Yeah, here, minus 55.84, right? So the angle, you have to take the angle, subtract from it an additional 30 degrees. And then you have to take the magnitude, 278.9, and multiply it by the N high voltage over N low voltage, multiplied by square root of 3, which in this problem happened to be the 10 times square root of 3 that we were talking about. That gave us a bit of a problem. For me, this has to be 5.88. Okay, but that's what we did. We multiplied by that gain. So the current increased to this value. Now I have the current and voltage brought to the secondary side, and I have one impedance. So I have, now my circuit looks like this. I have a voltage source, one impedance, and I have a load here that I know the voltage across it, I know the voltage here, I know the current. So if I know the current, I need to take that current multiplied by this impedance, which is the 0.21 divided by 3, because it was a delta impedance of the transformer as seen from the primary side. So I took that impedance and divided by 3. So it was a 0.21. So 0.21 divided by 3, which is a 0.07. Right? That's the J.07. Multiply that by the current, then add to it the voltage across this load that was transferred from the secondary side to the primary side, and that will give us the generator's voltage. That's the generator voltage, and that's the generator phase angle. Okay? What else are they asking for? Then they calculate the generator power. They took the generator voltage multiplied by the current conjugate. The current is the same as what we calculated before, right? Since it's just a simple circuit with a source and an impedance. So the current is the same that we calculated before. And then to calculate the full generator power, the three-phase generator power, they just took that, whatever they did here, and multiplied it by 3. And the phase shift of the generator voltage is 27.77 degrees. So with respect to the output. Okay. So the problem is not, the wording of the problem is not very nice, but it covers everything we wanted to cover, right? So it covers this star delta phase shifting. It covers the idea, the difference between the actual turns ratio and the terminal voltages in a star delta transformer, right? In a star star or a delta delta transformer, the ratio of the terminal voltage is the actual turns ratio. In a star delta transformer, the ratio of the turns voltages is not the actual turns ratio of the physical transformer, right? So, is this clear? Yes, ma'am.
I'm just double checking.
Double check.
Okay. What you want us to use, technically, that's the physical turns ratio.
Not what I wanted to use. What you have to substitute in the equation
Yeah.
is this n high voltage or n primary over n secondary is the physical turns ratio.
Okay, not primary.
So n primary over n secondary is the physical turns ratio. Whenever you go back to your equation, this is the physical turns ratio. It is not the terminal voltages, unless I'm talking about a star star or a delta delta.
So
If it's a delta star or a star delta, then you have to figure out what this actual turns ratio is.
what should we call the other turns ratio?
Fictitious turns ratio, the equivalent turns ratio. They call it T. I don't know, they call it T. They call the actual turns ratio A, or the physical turns ratio A, and they call the other one T, sort of an equivalent turns ratio. In a delta delta transformer, T is equal to A, right? And in a star star transformer, T is equal to A. But in a delta star or a star delta transformer, the T is not equal to A. T is equal to A multiplied by this phase shift and considering the square root of 3. Okay? So the wording of the problem will define if I gave you the turns ratio or not. The wording of this problem was very poor. I will have to be very clear. You are given 3 single-phase transformers with a rating of XYZ. These single-phase transformers are used to build a star delta transformer whose terminal voltages are XYZ. In that case, fine, it's very clear, right? The problem given here was not very clear, right?
So the problem you gave us would be just the n primary over.
We did it both ways, right? We did it both. Yeah. If I'm giving you 3 single-phase transformers with certain ratings, then I've given you n primary over n secondary, right? If I told you the single-phase transformer terminal quantities are 10 kilovolts to 100 kilovolts, they are used to build a delta star transformer. Then you know automatically that if the single-phase transformer was 10 kilovolts to 100 kilovolts, that means this single-phase transformer on the primary side has terminal voltage of what? 10, because it's a delta. On the secondary side, it's 100 multiplied by square root of 3. That's the terminal voltage, right? To get the turns ratio, you take that 100. If I tell you, no, you are given a 3-phase delta star transformer with a terminal voltage of 10 to 100 kilovolts, then what is the actual turns ratio of the transformer? No. No, that's where you have to consider the square root of 3. It's 10 over 100 square root of 3. That's the actual turns ratio. That's this n primary over n secondary that you have to substitute in the T. Okay? The wording will define what you use, right? Okay. Another example. Also confusing, probably. But this one's in per unit, yeah. Okay, 3 single-phase, 2-winding transformers. So here they tell you 3 single-phase, 2-winding transformers, each rated for 400 MVA, 13.8 to 199.2 kilovolts. Right? So in this case, the single-phase transformer is 13.8 primary, 199 secondary. So the turns ratio is what? 199.2 over 13.8. Here they gave you the actual turns ratio, right? And with a leakage reactance of X equivalent 0.1 per unit. Here they give you the impedance in per unit, right? So delta star delta does not matter. It's the equivalent, the impedance in per unit. As long as the impedance is in per unit, and you're going to derive your per unit equivalent circuit, and you are properly going to choose your bases such that the ratio of the bases is equal to the ratio of the terminal voltages of the transformer, then the X, you don't have to, even if they tell you star star, delta delta, star delta, I don't care. The X does not change because it's in per unit. Not like the previous problem where I divided by 3 because I was in real, I drew the single phase equivalent circuit in real quantities, not per unit. Okay? So now we have a few given things. So if I want to draw the single, I'm going to draw the single phase equivalent circuits. I know that I will draw 0.1 per unit in the single phase equivalent circuit. I know, right? That is given. And I can put it on the primary or secondary side. Does not matter, right? Because I will choose my basis properly. Okay, so these are connected to 4, and I know my single phase power. If I'm solving everything in 3 phase, and I have to take then S 3 phases 3 times the S single phase, right? If I'm going to choose my bases and solve all the equations in single phase quantities, then I can use 400. If I'm going to solve everything in 3 phase, then I will use 1200 MVA for the rating of the equivalent transformer, right? So it's depending on what you saw. We will solve typically in single phase. Anyway, so connected to form a 3-phase bank. Winding resistances and exciting current are neglected. That all the shunt impedance are neglected, and all the resistances are neglected. So you just have the series impedance, which is the JX.1 per unit. The voltage and the high voltage windings are connected in star. Okay, so the high voltage is always star. They're telling you that the high voltage is star. A 3-phase load operating under balanced positive sequence condition on the high voltage side is consuming, of course, 1000 MVA at 0.9 power factor lagging. So I know everything on the load side. This is 1000 MVA. So I know S. I know the power factor. So I can find out P, and I'm given voltage as well. This is the single phase voltage of the load, right? VA capital N, right? Single phase voltage of the load. Determine the voltage VAN at the low voltage bus. So they want the phase voltage on the low voltage side if the low voltage windings are connected in star, or to complicate it, connected in delta. If they are connected in delta, then what? When you solve the single phase equivalent circuit, you will get VAN, yeah, you will get the phase voltage, yeah. Because we're solving a single phase equivalent circuit. But if I tell you after that, what is the voltage on the actual voltage line to line on the delta? Yeah, I have to consider the root 3 and the phase shift between the star and the delta. So that's we'll see what we did here, what we'll do here. So of course they complicated when they add the delta. But okay, so let's see what we are going to do. So let us draw the problem, the givens. So we have these bunch of single phase transformers whose so S is 400 MVA for the single phase transformer. And the rating of the single phase transformer is 13.8 to 199.2 kilovolts. This is for the single phase transformer, with the X equivalent per unit equal to 0.1 per unit. Right? This is what we are given about the single phase transformer. Okay? This transformer is now going to be used to construct a 3-phase system. So star will always be on the high voltage side. One time we will construct a star-star transformer, and one time we'll construct a delta star transformer. Okay, so this is 1, this is 2. And then they will ask for a few things, basically. So, and we were given the load data. So the load was what? The load was 1000 MVA. So we have a load. So we have a generator here, a transformer, same, and a load. The load that we have here is so the load is 1000 MVA at 0.9 power factor lagging, with a phase voltage of 199.2 angle 0. kilovolts. Okay. So what's the equivalent circuit? Again, single phase equivalent circuit. Source. I don't have a source impedance, right? I have a source. And then what? I have a transformer. That's now it's a star-star transformer, so I don't have any phase shift, right? So I just have to put the transformer's impedance, and then I have a load. It's exactly the same as the previous circuit, right? So what do I know? I know a lot about the load. The load is 1000 MVA, 0.9 power factor lagging. I know the phase voltage at the load. So I actually know this voltage in the single phase equivalent circuit is 199.2 angle 0. But remember, I'm giving the impedance in per unit, so I'm probably going to have to solve this in per unit, right? So let's see. So I will have to find a base for the voltage and convert this to a per unit quantity. And one good, if you want to solve in three phase, so what they chose. So they chose the bases here. Using the transformer bank ratings as base quantities, then S base is 1200 MVA. This is S base for the three-phase system, right? And we said that we will typically choose S base three-phase, and we will also choose line-to-line voltage base somewhere. And anytime we see a transformer, we have to change that base based on the ratio of the terminal voltages of the transformer. Okay, so the line-to-line voltage base is going to be 199.2 multiplied by square root of 3. That is the line-to-line voltage of the transformer. Right? So they told us that the transformer phase voltage is 199.2. So its line voltage is 199.2 times square root of 3. So they chose the transformer's terminal voltages as the base on the transformer side. Right? So they chose this to be the base on the high voltage side. If I'm going to draw my single phase equivalent circuit, I'm going to have to use my single phase voltage base to find the equivalent per unit voltage on the load. Right? So this is my line-to-line voltage base. So what is my phase voltage base on the high voltage side? Yeah, 199.2, which means that the voltage here is going to be, in my single phase equivalent circuit, the voltage will be 1 angle 0. 1 angle 0. This is the voltage on my load. Okay? And that's what they started with here. They said that the VAN in per unit is 1 angle 0. That's where that came from. Okay? They also calculated the base current since we were given, basically I think they're asking for the generator voltage. They're asking for the same thing. They're like the same thing they asked for in the previous problem. So they're asking for the generator voltage. So now given that the load is 1000 MVA, right? This is the power of the three-phase load, right? That's why if I want to calculate the current, I have to make sure that the per unit, if I'm going to convert this to per unit, then I have to use S base three-phase as the base value to convert this to per unit. Or I can divide this by 3 and use 400. And in that case, I will be using my single phase, right? So because remember, S is equal to 3 V phase, I phase, right? And this applies for actual quantities or base quantities. S base is equal to 3 V phase base times I base. I base doesn't matter if it's line or phase because we're talking about star connected systems here, right? So, or it's equal to square root of 3 V line times I phase or I line, because it doesn't really matter because it's a star connected system, right? So if I want to calculate the current, I can use the line-to-line voltage base and the three-phase power, right? Or I can use the phase voltage base and take the three-phase power and divide it by 3, which is, we go back to the This is the three-phase base power, then divided by 3, we go back to the 400, right? So you have to be careful what you're using for the calculation. So you either use, so S here will use the 1200 if I'm going to keep the 3, right? So S 1200 is equal to 3 times V phase base, which my V phase base would be the 199.2. And then I can calculate the current. Or I use S, which is 1200, is equal to square root of 3, and I use my V line-to-line voltage base, which in this case is 199.2 multiplied by square root of 3, and I calculate my current. So here they took the S, which is the load, the power of the load, and they want to calculate the current. So they divided by the S by 345 times square root of 3. 345 times square root of 3. So 345 is what? Is my line-to-line voltage base. They took the line-to-line voltage base, multiplied by square root of 3, right? And then they took S and divided, and S divided by square root of 3 times my line-to-line voltage base. Right? So S divided by square root of 3 times line-to-line voltage is equal to what? Is equal to the current, the phase current IA. Okay, so that's how you calculate the current. I have the load power, I have the power factor, I have the load angle. I can calculate the current. They chose to calculate the current in this fashion, so they took, and then they converted it to per unit by multiplying also by the base current. Sorry, that's an additional thing. So this is actual current, right? 1000 divided by V line to line. Yeah, divided by V line to line times square root of 3. So 1000 divided by V line to line. What's my line to line voltage? It's 199.2 times square root of 3, which is 345. Right? So 1000 divided by 345 multiplied by square root of 3. That's the actual current. This is IA actual. And then they had originally calculated the base current. How do you calculate the base current? Base current is from the base power divided by the base voltage. The base voltage here happens to be equal to the actual voltage, right? It just happens to be, but they can be different here. So they took the actual current divided by the base current to calculate the per unit current. So 0.8333. Right? So then we are able to calculate this current. This is 0.833, angle of minus 25 point blah blah blah. Right? So I have now this current, which is here. I have this voltage, which is here. I have this impedance, which is JX.1. Then how do I calculate this voltage? So this voltage, 1 angle 0 plus the voltage drop across this impedance. Same thing. So VAN, which is generator voltage, is equal to VA capital N, which is the 1 angle 0, plus JX equivalent, which is the 0.1, right? Because we're in per unit, multiplied by the current, also in per unit. Okay? Then they calculated the generator phase voltage. It's okay? Yes? No? Let's see. What else they want? So this was in per unit. I guess they're converting it back to actual values to help confuse us even more. So how do you convert from per unit to actual values? You have to multiply by the base. The base where? In that zone. Right? So we had a transformer that had a base voltage line to line on the secondary side, because it was the star's base voltage equal to 199.2. What was the square root of 3? The line to line voltage was 199.2 square root of 3. Right? That was the base voltage on the secondary side. What's the base voltage on the primary side? Multiplied by square root of 3, because it's a star-star transformer. That's the line-to-line voltage base. The single-phase voltage base, remember, now it's all confusing now. So now the line-to-line voltage base is 13.8 times square root of 3. But I calculated the phase voltage in per unit. For me to calculate the phase voltage in actual values, I have to multiply it by the phase voltage base. Right? If I'm doing my calculations in line to line, then I multiply by the line voltage base. If I'm doing my calculations in phase, I have to multiply by the line voltage base. If I'm doing the calculations in line to line quantities, using the line to line voltage base, then I have to find the actual value by multiplying by the line voltage base. If I'm doing my calculations in phase, like I did here, then I would have to multiply by the phase voltage base to convert to actual quantities. Right? So the phase voltage base is going to be 13.8 in this case. Right? So since the line-to-line voltage base is what? Yeah. V base X line to neutral, right? Ln means line to neutral. So the phase voltage base on the primary side is 13.8. It is not 13.8 times square root of 3. Okay? Because we're talking about phase quantities. So we took the actual quantity and multiplied by the base quantity, and we got the we took the per unit quantity multiplied by the base, and we got the actual quantity. Okay? Any questions? So please attempt to do the second one. The only difference is the phase shift and the base value. Right? So can you please try to do it? So remember, the 1 angle 0 does not change. The 0.833 does not change. The voltage and the current of the load do not change. Right? They do not change. But since I have a delta star transformer, the star leads by 30. Right? The star is leading by 30 degrees. So what do I do to convert? I want to bring these to the primary side and do the same thing that I was doing. Right? I will do the same thing. I just have to take this 0.833, angle minus 25.84, subtract 30 degrees. Bring it on this side. And take this 1 angle 0, subtract 30 degrees. Bring it on the other side. Right? And I do the same thing. Same. After I bring it on the one side, I do the same equation. I get the phase voltage in per unit. Then we have to figure out, since it's connected in delta, right? What is the base? Do that, and we can discuss it last time. That's just do that. I mean, that's just make sure that you choose the base voltage on the primary, the ratio of the base voltages to equal the ratio of the terminal voltages, and you will find that the base voltage, the single phase base voltage, will be 13.8 divided by square root of 3. Okay, so the ratio of the bases is going to equal the ratio of the terminal voltages. The terminal voltages now is 199.2 times square root of 3 on the star side. But what is the terminal voltage on the delta side? It's 13.8, not square root of 3. Right? That's why now that was the ratio of the terminal voltages. So that when you trying to find the base, it will be 13.8 divided by square root of 3. Do that. Just do the ratio of the terminal voltages equal to the ratio of the bases. We have the base on the high voltage side, which is the line-to-line voltage base, 199.2 times square root of 3. What is the base on the low voltage side? Just the inequality. And that's the only difference about it.